Assalamu alaikum students, welcome to a new lecture of engineering fluid mechanics, and in this lecture we are going to talk about the reaction turbines. In the previous lecture we talked about the impulse turbines, and one thing that we found out that they are most efficient for lower flow rates and higher head operations. So whenever we are going to use an impulse turbine, we must have an higher head and a lower flow rate. So in that case, our impulse turbine will be the most efficient, or in that scenario we will select an impulse turbine to function and generate hydroelectric power. Reaction turbines, on the other hand, are best suited for higher flow rates and lower head situation. So whenever you have a lower head and a higher flow rate, so the best suited turbines are the reaction turbines, and the major purpose is to generate electricity. So mainly we use two types of reaction turbines for generating electricity, and that is the Francis turbine and the Kaplan turbine. Francis turbine is a radial flow or in some cases a mixed flow turbine, while Kaplan is an axial flow turbine. The type of the point on which we classify these two turbines is the direction of the fluid and the axis of the rotor. So in the Kaplan turbine, in the Francis turbine, the flow is radial to the rotor, as the flow enters through the guide vanes into the rotors. It is in the radial direction, while in case of the Kaplan turbine, when the flow enters the rotor, it is parallel to its axis. So here you can say that is why we call it an axial flow turbine. So they are both named after James B. Francis, an American engineer, and the Kaplan was named after Victor Kaplan, a German professor. So and Kaplan is an efficient axial flow turbine, and the reason is that its guide vane and the rotor blades are adjustable. So as you can see in this figure right here. So today we are going to talk about these two turbines, or we will more have an overall view of how we are going to represent the head, the flow rates, and the efficiencies in case of our reaction turbines. And we will more so do it in the form of our dimensionless analysis that we performed for our pumps, and in that way we have our coefficients for our head, our flow rates, and the dimensionless parameter, that is the efficiency. So we are going to look into that for these two turbines. So this is what it is already covered, and now we are going to talk about the dimensionless parameters. And one thing that we discussed about the dimensionless parameters is that once you have these coefficients, the flow coefficient, the head coefficient, and the power coefficient, so you can see that these equations contain terms that are geometric. So flow rate is normally a thing that is associated with a fluid flow, but you can also associate that flow rate with a geometric term, and that geometric term in this case is the diameter of the rotor, the overall diameter of the rotor. So also the head coefficient is also associated with the diameter, and similarly the power coefficient is also associated with the geometric parameter, that is the diameter. So you can see now from these equations that these are dimensionless, so we can use them from any geometry. It can be a small rotor, it can be a big rotor, but in both these scenarios we will be using the same equation. So we are basically equating the flow parameters of a fluid to the geometric parameters of our impeller or the rotor that we are going to use for different flow situations. This is how they are done with the help of these coefficients, and that's why they are so important when it comes to the seeing the performance of our turbines. Or even in case of pumps, we also saw these flow coefficients, head coefficients, and power coefficients, and efficiency for our pumps also. So these are also applicable for our pumps. So that's why they are so necessary for us to apply. And now we are going to talk about selecting our turbine, that how we are going to select our turbine and what will be the parameter that we are going to look into. So for geometrically similar turbines and for negligible Reynolds number and surface roughness differences effects, the relationship between dimensionless parameters are given by these equations that are shown right here. So basically you can compare your head coefficient with your flow coefficient, your power coefficient with the flow coefficient, and the efficiency with the flow coefficient with the help of these pi terms that we know that come from our Buckingham pi theorem when we apply the dimensional analysis. So these are dependent on the type of turbine that is involved. So these pi terms are basically related to which type of turbine we are going to use. Either it will be a Pelton wheel, that is an impulse turbine, either it can be a Francis turbine, or either it can be an axial flow turbine. So this is when we are going to choose these three pi terms. So also for turbine efficiency is related with the help of this equation to the power coefficient and the head and the flow coefficient. So as we discussed just now, we need a parameter with the help of which we can select our turbine, and the best one is the power specific speed, and that specific speed is inversely related to the overall head. So from this you can get a relation between the rotor specific speed and the available head, and with the help of the shaft power that is required, and the density and the gravitational acceleration and the angular velocity, we can actually make this equation. And if we had all this data, we can calculate the value of this power specific speed, and based on that value we can actually select our turbine. So as indicated above, the design engineer has a variety of turbine types that are available for any given application. It is necessary now to determine which type of turbine would best fit the job. So, and the best fit is the most efficient. So before detailed design work is attempted, as with pumps, the use of specific speed parameter can help provide this information. Remember that we also use this specific speed parameter when we were talking about pumps, and how we were using different specific speed to select different type of pumps. So for hydraulic turbines, the rotor diameter is eliminated between the flow coefficient and the power coefficient to obtain the power specific speed. So this parameter will actually another dimensionless parameter which will give us the type of turbine that will be best suited for our given conditions. So we use the more common but the non-dimensionless definition of specific speed, and this is not a dimensionless. So another term for specific speed, and here the n dash and subscript SD is calculated with angular velocity in RPMs, the shaft power that is in brake horsepower, and the actual head available in foots. So optimum turbine efficiency for large turbine as a function of a specific speed is indicated in this figure that we are going to see right now. Also shown are representative rotor and casing cross sections, and now let's have a look at that figure and then explain the rest from that. So this is the figure that they are talking about, and as you can see, this term right here was inversely proportional to our head, and we saw that for an impulse turbine we need a higher head. So a higher head means that we will have lower specific speed. So that's why the impulse turbine lies in the front of this other selection that we have So as the specific speed increases, we move from impulse turbine to the reaction turbine. So for moderate specific speed, we can use our Francis turbine, and when we talk about the higher specific speeds, we actually talk about the axial flow turbine, that is our Kaplan turbine. And from here, this figure, we see that the specific speed and the efficiency is plotted, and for impulse turbine, the higher efficiency is right about in this region, that is at very low specific speed. Francis turbine can have higher efficiencies at a higher specific speed, but overall the Kaplan turbine is the most efficient, as you can see from this figure, that at higher specific speed the Kaplan turbine is the one with which is more efficient, and that also for a very low head. So that is why they are very efficient for lower head applications. So from this figure you can actually see the overall the turbine cross section and the maximum efficiency as a function of specific speed from these two figures right here. So now we are going to see an example with the help of which we are going to see that in which scenario we are going to select our turbine. In a certain scenario, we are required to select a turbine type. So given is a hydraulic turbine that is to operate at an angular velocity of 6 revolutions per second, a flow rate of 10 cubic foot per second, and a head of 20 feet. So note that the head required is 20 feet. So now what we are going to do, we are going to calculate the specific speed, because this is the parameter that we use for selecting a turbine. And using the information in figure 12.32 to use the dimensional form of specific speed indicated in figure 12.32, we must convert the given data into appropriate units, and for the rotor speed we get 360 rpm from 6 revolutions per second. To estimate shaft power, we assume the all available head is converted into power and multiply this amount by an assumed efficiency 94%. So here the efficiency is assumed, and we calculate our shaft power, and it comes out to be 21.3 horsepower. Thus, for this turbine now we can calculate our specific speed, and that comes out to be 39.3, sorry. So according to the information of figure 12.32, a mixed flow Francis turbine would probably give the highest efficiency, and an assumed efficiency of 0.94 is appropriate. So this term can be read from the figure that we saw previously, and from that we can see that a mixed flow Francis turbine will be the suitable for the conditions that are given to us. So now let's have an argument, and let's say that we wish to select a Pelton wheel for this given scenario. So how will the geometry of the Pelton wheel change, and we are going to see that will it be practical to actually use a Pelton wheel in this situation. So note that only a 20-foot head and the maximum jet velocity V1 obtainable neglecting the viscous effect would be this much, the 35.9 foot per second for the given conditions that are given to us. So the velocity, the jet velocity will be this much, and as shown in equation 12.52, for maximum efficiency of a Pelton wheel, the jet velocity ideally 2 times the blade velocity. So V1 should be equal to 2 omega r, and the wheel diameter d is equal to 2r, judging from this equation. So we are going to find our wheel diameter, and to obtain a flow rate that is 10 cubic foot per second at a velocity of V1, the jet diameter can be calculated, and it comes out to be 0.596 foots. So now we have our jet diameter and we have our rotor diameter. So now we are going to compare those two and have a discussion that can we have this kind of a Pelton wheel for this flow rate. So as you can see, the Pelton wheel diameter is 0.952 foot, supplied with a water through a nozzle diameter d1 0.596. So let's say that the diameter of this rotor is 0.952 and the diameter of this nozzle is 0.596 foot. So these two numbers are not that far apart. So, and here visually we see that the rotor diameter is very large from this nozzle diameter. So this nozzle diameter, if it is a small d, it is very small than the rotor diameter. So basically this number is not practical. It is not practical at all, even if you are using multiple jets. And the maximum we can go is that, let's say we place 8 jets, the diameter would be 0.211 foot. So 0.96 foot is too much large and it is not practical. So hence the above calculations reinforces the result in figure 12.32. A Pelton wheel would not be practical for this application if the flow rates were considerably smaller. The specific speed could be reduced to a range where a Pelton wheel would be the type to use. So basically we have to adjust the flow rate to actually use a Pelton wheel in that scenario. So right now it is not feasible.